Good day, everyone. What is power integrity? In our previous video, we covered power integrity, focusing on strategies like managing voltage drops, reducing noise, and utilizing decoupling capacitors. These practices are essential to maintain a stable power supply and avoid disruptions in high-speed circuits. With power integrity covered, let's now focus on high-speed signals in PCB design. Introduction to high-speed signals. In modern electronics, high-speed signals are crucial as devices become more complex and data transfer speeds increase. Let's dive into the basics of handling high-speed signals in PCB design. Now we'll dive into the concept of high-speed signals and their significance. What are high-speed signals? High-speed signals typically range from 50 MHz to 3 GHz, including clock signals. For accurate signal transmission, we rely on transmission line methods, especially if the track length exceeds the signal's wavelength. Next, we'll examine the different categories of high-speed signals. Types of high-speed signals. There are three key types of high-speed signals: single-ended, differential pair, and clock signals. We'll begin by discussing single-ended high-speed signals. Single-ended high-speed signals. Single-ended signals travel along a single trace, reference to a common ground. These signals are typically used in digital communication systems. The impedance of the trace is usually 50 ohms, ensuring a stable and controlled signal path. Moving on, let's explore differential pair signals and how they function. Differential pair signals. Differential pair signals are transmitted through two complementary traces. These traces carry equal and opposite voltages, which helps cancel out noise and improves signal integrity. The typical impedance for differential pairs is 100 ohms, commonly used in high-speed interfaces such as USB and Ethernet. Now let's look at clock signals, which play a crucial role in synchronization and data timing. Clock signals. Clock signals are crucial for synchronization. Single-ended clocks are often used in legacy systems, while differential clocks offer better noise immunity in high-speed systems. Now we'll take a closer look at the most common high-speed signals. Common high-speed signals. In today's high-speed electronics, several signal types play a crucial role in efficient data transmission. Let's explore some common high-speed signals and their functions. First on the list is HDMI, which is widely used for video and audio transmission. HDMI transmits uncompressed video and digital audio, replacing older analog video standards. It uses differential signaling to ensure reliable data transmission over longer distances. Another common signal type is MIPI, which is used in mobile devices. Let's see how it works. MIPI. MIPI is a serial communication protocol used in mobile devices, including CSI for camera to processor and DSI for processor to display. It uses differential signaling for video signal transmission to ensure high data integrity. Now let's examine DDR signals, which enable fast data transfers in high-performance systems. DDR signals. DDR signals enable fast data transfer between the memory controller and memory modules, synchronized by strobe and clock signals. These signals are crucial for high-performance computing systems. We'll now address some of the challenges encountered in high-speed signal design. Challenges in high-speed signal design. Designing high-speed signals presents several challenges, including signal integrity, crosstalk, and routing complexities. To overcome these challenges, let's explore some of the best practices that can help improve high-speed signal design. Best practices for high-speed signal design. So, to improve signal quality, follow best practices like maintaining controlled impedance, minimizing trace length, proper grounding, avoid sharp corners, and proper layers stack up. In summary, let's review the key takeaways from high speed signal design. Mastering high speed signal design is crucial for optimal data transmission. By understanding signal types like single ended, differential pairs, and clock signals, you can ensure efficient PCB layouts. Key practices like controlling impedance, minimizing trace lengths, and grounding effectively maintain signal integrity. In the next video, we'll explore the fundamentals of impedance matching, focusing on key strategies to ensure optimal signal integrity and enhance the performance of your high-speed circuits. Don't miss it. Thank you for watching and stay tuned for more in our Back to Basics series.